Hello, welcome back to my channel. And this is the third lecture in quantum mechanical course. Last time we understood about quantum mechanics and what Schrödinger equation gave us, what is a wave function is, and how do we make any physical interpretation out of the wave function. And last time we understood we have this wave function, and wave function gave us a probability density function, probability distribution function. We can get some physical information out of it, especially about the particle position. So one of the thing people ask, where was the particle before you make the measurement? The Bohr's principle tells us that the probability of finding a particle between A and B is the integration of this probability density function from A and B. But the question a lot of people ask, where was the particle before you make the measurement? So the question is, last time we had this probability density function, which could, and this is my x-axis, and probability density function could look like something like this. It's just arbitrary drawing, but imagine I make a measurement and it come out at this position A. So the question is, where was the particle before you made the measurement? This is a kind of a valid question. We don't know the exact location of the particle, right? Because we have this probability distribution, which give us statistical information of the possible position of the particle. So the question here is, where was the particle before you make the measurement? Who gave try to give an explanation. One was the particle was at A, but if the particle was at A, then our theory is incomplete, because if the particle was at A, our theory was not able to predict it. So something is missing in our theory, and this was the point Einstein made. And the second was particle wasn't anywhere. A measurement force is to be there. And it's very weird interpretation of this rule, because we don't see such thing happening in classical world. So this is very fascinating and weird. And the third one, the question don't have a meaning, because you can never test this hypothesis, like where was the particle before you make a measurement, because this is metaphysics. So the question doesn't make sense. What was the answer to this question? This is where John Bell come in. So he came up with the theorem, which we can't understand at the moment. After we understand some of the quantum mechanics, we will go back to Bell's theorem and try to understand all this again. But in summary, this Bell's theorem tells us that there's no hidden variable that could make theory complete. So you have to get rid of this Einstein notion where you think the theory is complete and it's not able to predict even though the particle was that A before you make a measurement. And the third one, Bell's theorem also tells us that particle position do depend where the particle was before. And we are left with this interpretation where we say the particle wasn't anywhere, measurement force is to be there. And it is very weird and very fascinating, but this is what most of the most accepted answer in quantum mechanics. People still debate about it, but we follow this rule where we say particle one and anywhere. When you measure it, you force it to be there, and it is weird, and it's hard to come around using this kind of notion in physics, but we have this and we use it. So I hope you like this video. If you do, give the thumbs up, and I will see you next time.